So for this section, we're going to shift gears a little bit and talk about something that's a bit more abstract. I'd say looking at the law of sines and cosines, I think that's a bit abstract in itself, but matter of taste. I do think this is a bit of a shift, at the very least, where we're going to talk about polar coordinates, the polar plane, polar representations of points and equations. And no, this does not mean that we're talking about equations and points that are particularly cold. What we're looking at here instead are representations built around straight line distance and rotation, where what we're probably more used to, what we've probably seen the most, is the rectangular coordinate scheme, the x, y coordinates, where we're talking about things strictly in terms of straight line movement along an axis, be it horizontal for x, vertical for y, or if you get into 3 dimensions, I don't know what the word is for a 3rd dimension, but here we'll think about it as approach and retreat, where we're moving either out or further in, as it were. But the rectangular plane is about those straight lines along our axes. And another name for this that you may have heard is the Cartesian plane, Cartesian coordinates, so named for noted philosopher and mathematician and Captain Cook impersonator René Descartes in, I believe, the 16th century. So there's a lot of the work in terms of codifying this coordinate scheme that you've probably seen a great deal, you've spent most of your time working with in algebra, was done by French mathematicians around that time. But it's not the only way that we can think about position. It's not the only way we can think about location. We could also think about it in terms of radial distance and rotation, in terms of what are called polar coordinates, where the idea of polar coordinates actually dates back to the ideas of thinking about trigonometry. That is, it dates back to the ancient Greeks, although they didn't really codify a strict point location scheme. The idea of coordinates actually didn't come into place for more than 1,000 years after, at least not technically. And in some sense, it's viewed that the polar coordinate scheme in particular was built in response to rectangular, but it's an argument for a math historian. Point is, this is something that's kind of, in a way, older than rectangular coordinates. It's an older way of thinking about location, where instead of talking in terms of movement in single dimensions, we build everything around spin. And for this, we're talking about our point in terms of that spin with a horizontal axis that we call the polar axis. And the end of it, we get a ray that comes out to form our pole, which kind of sits at a origin point, if you think about it in the same sort of language as rectangular coordinates, where for these types of coordinates, we have that radius type measurement r, that in this case can be positive or negative or 0. It's just a measurement of straight line distance from that pole, from that origin point. And we talk about angles theta in the same way that we did in chapters 4 and 5 and 6. That is, if we rotate counterclockwise, it's taken as positive, and clockwise is taken as negative. And you might look at this and say, well, why do we care about it? Why is any of this interesting or worthwhile or worth spending any amount of time on? And the reason why this might be something to see is because, well, there are limits to how we see things in terms of rectangular coordinates. For example, one of the most traditional and important geometric shapes, the circle, in particular the unit circle, x squared plus y squared equals 1, is not a function in rectangular. You can't put this in terms of just x or just y and describe the whole thing. If you remember what the unit circle looks like, it very much, by definition and repeatedly, will fail the vertical line test. So if you want to think about this in a functional way, you really can't without making some serious restrictions and rearrangements. It just doesn't happen. But we're going to see later that there are some really nice ways that we can instead talk about this in terms of polar coordinates, because a polar coordinate system is designed perfectly for talking about rotation, for talking about circles and circular movement, for being able to generate and look at things in a lens that we really can't for rectangular equations, at least not without seriously having to adjust our frame of reference. But the first thing we're going to see here, what we're going to see next, is a couple more examples here on how we can represent points, how we can plot points in the polar coordinate scheme in terms of that radius r and rotation theta.